All right, how's it going? Welcome back to another video here in the series on linear algebra. You may have noticed that the section title has finally changed, right? We have been talking about eigenvalues and eigenvectors for a little while now. But nevertheless, every section, regardless of how long it is, needs to come to a close. And we are on this new section here called Quadratic Forms and Conics. Okay. And just to give you a little bit of context for how this section is going to go, and clearly it seems like there are two main goals, or two main topics to understand in this section. The first being on quadratic forms and the second being on conics. So naturally, it's going to make sense that the first video that we make, or in this section at least, being this one, is going to be on quadratic forms. And then the second of two videos in this section is going to be on conics, or conic sections. Okay. So that's going to be the general structure. And just to give you an idea for what we're going to be doing specifically in this video, besides just talking about quadratic forms, we're going to first introduce what they are, just conceptually, because right now we probably don't have a great understanding of what quadratic forms are. And then we're going to show how we can decompose matrices to be able to rewrite quadratic forms in a more simpler manner. And the way that we're going to do that is going to build off of the last section on diagonalization of matrices. Okay. So kind of a shorter section, but still something very useful. Quadratic forms and conics have applications in various areas of applied math as well as physics. I can definitely say that when we do get to the first physics video series on this channel, we will be talking about different types of conic sections when describing, I shouldn't say particles, but just objects in space that are orbiting around each other, like orbital mechanics. Okay, so stuff is still useful even though the section is shorter. All right, so hopefully that makes sense. First thing that I'm going to do is I'm just going to write out the definition for the central object of this video, which is the quadratic form, and then we're going to go through that together. All right, so this is the main definition of the video, so it's worth going over. So let's go through it together. It says here, this is the definition for both sesquilinear, Hermitian, and quadratic forms. So three different quantities, but the main focus of this section is going to be on, or of this video I should say, is going to be on quadratic forms. We'll show how these first two quantities relate to quadratic forms, even though the first two are more general versions of the quadratic form. So still, let's go through it together. It says here that starting with a sesquilinear form is simply a quantity that looks like this. So we can denote it as f, where in this case f is just a scalar, and f is expressed as a product of three different quantities. The first is the Hermitian conjugate of some vector x times a matrix A times a vector x. Okay, so any scalar of the form x dagger ax is considered a sesquilinear form. This is the way that we would write out that sesquilinear form in matrix vector notation. But if we were to use Einstein's summation notation, this is what it would look like, where now instead of a matrix A being written like this, we can just denote its elements generally as A sub ij, just being the element in the ith row, jth column. And rather than writing out a vector like this with the little arrow on the top, we can just write out the vector component, x sub j. And then in order to take the conjugate transpose, first just to take the conjugate part, that's what we're doing with the star up here. And then in order to take the transpose, that is going to take this matrix vector product, which equals a resulting vector. And when we take this row vector times a resulting vector, we end up getting a scalar. And the way that we can get a scalar in Einstein's summation notation is by making sure that we have no indices that appear a single time. So by forcing this index to be I right here, now we see that there are 2 factors of I, 2 factors of j, so all of the summation indices get summed over, and that's why we're left with the scalar. And that's how we can write this quantity out here in that notation. All right. Now, I think what I want to do, because that can already be a lot in itself to unpack, before we go on to the rest of the definition, I want to make sure we understand what is going on here. Because it hasn't been super long since we've discussed what the Hermitian conjugate was. That was actually just in the most recent video, right? So in the general case, let's suppose that, let's first write out this quantity, this sesquilinear form right here. F equals x, not transpose. I want to keep this general, right? So F equals x, a dagger, times a matrix A, times a vector x, like this. So just to make sure that we understand what's going on, we're going to put dimensions on each of these, and we'll be general. So we'll suppose that A is an n by n matrix, x is a vector, and in order to multiply this vector by this matrix, we need to make sure the inner dimensions match. So this would be an n-dimensional vector. You see that the inner dimensions match right here. And then this quantity, x dagger, is just going to be the conjugate transpose. So the dimensions are going to be swapped rather than being a column vector like what we have right here. This is a row vector. And then if we were to just apply this product of 3 different quantities right here, let's see what the resulting output dimensions are. So we're going to start with a times x, right? And the inner dimensions match, leaving us with the outer dimensions as the dimensions of the resulting quantity after we take the matrix vector product. And we can just look at those, and it's going to be n by 1, right? And obviously, if you take a matrix times a vector, we're just going to get another vector. Haven't done anything with this yet, so this is just x dagger. Still has dimensions of 1 by n. If we were to call the resulting vector that comes from this matrix vector product, maybe we'll say a times x equals some other vector y. So then this vector y is what you get when you take this times this. It will have dimensions of n by 1. And now we just apply the same process, right? Where we say, okay, do the inner dimensions match? They do, they're both n. And then the outer dimensions tell us what the overall dimension is of the quantity after we take the product. And that is just going to be 1 by 1. And that is this quantity f. So how we should interpret this is that a sesquilinear form is inherently a scalar quantity. Even though a lot of the objects in the linear algebra universe are vectors and matrices, these quantities are inherently scalars. Now, this is still, well, hopefully that makes sense. This is all still very general, right? We haven't provided any examples yet. And maybe just to quickly provide an example, let's just work with a 2 by 2 case, and we'll start to see how the idea of quadratic forms comes about, even though we haven't gone through that part of the definition yet. So let's just say that my matrix is a 2 by 2 matrix, and we'll keep it general. We'll just say A, B, C, D. X then has to be a 2-dimensional vector, maybe with components x and y. And then if I were to take the complex conjugate transpose of the Hermitian conjugate, I need to convert this column vector into a row vector, and now this is going to be x star, or x conjugate, and y star. Each of the components of this vector, we're going to take the complex conjugate of. And that's what f is equal to. If we apply the matrix vector product, we still have the row vector, x star, y star. And then the resulting vector from this quantity is going to be ax plus by for the top component. And the bottom component is cx plus dy. And then if we were to just take this row vector times this column vector right here, hopefully I'm not going too fast, it's going to be x star times this quantity. So let's write that out. We're going to have ax x star plus be x star y, and then we're going to add on y star times this quantity. So this is going to be plus cx y star plus d y star, like this. And that's what the quantity f would be equal to. And we see here that this scalar has a general property in each of the four individual terms that are being summed up. And that general property is that it's going to be some coefficient, meaning some element of our matrix, times two factors of the components of our vector, or its complex conjugate, right? So in this one, the two quote-unquote vector components are x and x star. Now we have x star and y, then x and y star, and then y and y star. And I should mention too that I chose the 2x2 case just to keep computations really short, but maybe try the 3x3 case if you're not convinced that even in the n by n case, you're going to have this giant sum of terms. Each term is only going to have two factors of a vector component. In this term, plus this term, plus this term, plus this term, in every single term in the summation. And this might be starting to hint at why there's a specific subset of these quantities called quadratic forms. There's inherently this idea of powers of two, like in a quadratic equation. Okay. So hopefully that makes sense. This is a general way of expressing a sesquilinear form. But what we can do is we can say, well, there might be certain sesquilinear forms that have specific properties, and those types of sesquilinear forms are given convenient names, which are Hermitian and quadratic forms. We'll start with the Hermitian case. While a sesquilinear form just has this general matrix A right here, Hermitian form is a quantity that looks like this, except now the matrix A is a Hermitian matrix, which means that if A is Hermitian, it's equal to its own complex conjugate transpose. Or in other words, say A equals A star, or Aij, the general element of the matrix is equal to its complex conjugate times its transpose. Yeah, we'll leave it at that, okay? And you can imagine that means only certain matrices are going to satisfy that property. So for the matrices that do satisfy that property, we call it a Hermitian form. And then finally, we're going to get to the last part of this definition, which is a quadratic form. And that is this sentence right here, where it says that now if the matrix A is real and symmetric, then F is a quadratic form. And this definition, even though just looking at the words, it might look very different from this definition, we can see that this definition is just a slight subset of this definition right here. A Hermitian form is just a slight generalization from a quadratic form. And that's the part that I want to make sure we understand before we move on to anything else. So, and I want to keep this up just because it's a general example, I guess. But for a Hermitian form, I don't know why I erased that. I want to use that. So let's just write this out here. Hermitian form. This is when the matrix satisfies Aij equals Aj complex conjugate, right? Now, in the quadratic case, we're saying that, which I'll write just below this, in the case where we have a quadratic form, then the matrix needs to be both real and symmetric. So that means that Aij equals Aji. That takes care of the symmetric part, right? But notice that part's already contained in the Hermitian form too, right? The fact that we're interchanging the indices. So we see that property of a quadratic form is contained within the Hermitian form. And then the other part of the quadratic form is that the matrix needs to be real. So that just tells us that all the elements need to be from the set R, right? That means that we also need to have that Aij is an element of the set R. And while this might seem like a different condition than what we have right here, we know that real numbers, when we take their complex conjugate, that doesn't change their intrinsic value. A real number is just a number of the form a plus 0 times an imaginary component. So whether we're adding 0 times I or subtracting 0 times I, we are not changing its value. So it turns out that all quadratic forms are Hermitian forms, but not all Hermitian forms are quadratic forms. In other words, these are more general than this. Just an example would be a matrix that is Hermitian but has complex numbers to them. They would still satisfy this condition, but they would not satisfy this condition because obviously they're not real, right? So hopefully that makes sense. And the reason why I'm trying to spend some time on that is because what we're going to do in the next whiteboard is we're going to make a statement about Hermitian forms, but the idea behind talking about Hermitian forms is that anything we say about Hermitian forms can also be applied to quadratic forms. Okay. So I'm going to erase the board and then we're going to go through that claim together. All right, so first claim of the video is that Hermitian forms are real. And what we're going to do is we're going to first go through proving this, but then see how that actually relates to quadratic forms before just talking about them a little bit more to see what we can really say about quadratic forms. I'm trying to be general, but I think probably just going through this and we'll see how this unfolds here. Okay. So starting with Hermitian forms are real, let's just prove that first. So that marker is hard to open. Yeah. I don't know if you saw that, but I really had to untwist that thing there, right? So let's say that we start with some quantity f, which is going to be our Hermitian form, and it's of the form x dagger hx, like this. And I'm writing H instead of a matrix A because for a Hermitian form, this matrix right here is a Hermitian matrix. So just using that as a reminder. Now, the way that we're going to prove that this quantity F right here is real is we're going to show that it's equal to its own complex conjugate. I wanted to say complex conjugate transpose, but the important part is its complex conjugate. Or in other words, we're going to show that F is equal to F star. Of course, again, the reason being because if F is A plus, let's do this, A plus 0i, right, that will equal A minus 0i. So that's going to be the condition. So to start the proof off, I'm going to just take this Hermitian form right here, F, and take its complex conjugate. So if I take conjugate of this, then I need to take the conjugate of the overall quantity right here. And as a next step, I'm also going to not just take the complex conjugate of f, but I'm also going to take its transpose, like this. And hopefully we're familiar with the fact that because f is a scalar, when I take its transpose, I'm not actually doing anything to a scalar. The transpose of a scalar is just itself. So f star transpose is still the same thing as just f star. We're not changing that. But the reason why I'm adding the transpose is because if I were to take the complex conjugate and the transpose of this quantity right here, now all of a sudden that becomes the Hermitian conjugate. So I can write x dagger, same thing in parentheses, so x dagger hx, but then rather than the complex conjugate, I'm going to write out the Hermitian conjugate. And now it's just a matter of applying the Hermitian conjugate to each of these terms in the product. And the way that we do that, of course, is we just interchange the order that they're written in and then apply the dagger to each of those terms individually. So we'd start with this quantity right here, which is just x, and then apply the dagger. It's a wide dagger. Let's see. Ooh. Something like that, right? X dagger. Then we would take our matrix H and apply the Hermitian conjugate. And then finally, we take our quantity x dagger, take the dagger of that. And then it's just a matter of simplifying. We can't simplify this first term right here. It's still just going to be x dagger. For this term right here, h dagger, we know that's going to be equal to just h because h is Hermitian. And by definition, a Hermitian matrix satisfies that the matrix is equal to its Hermitian conjugate. And then finally over here, when we apply the dagger 2 consecutive times, that brings us back to the original vector x. So what we see is that we started with f star, which was this quantity starred, and now we're left with just that same quantity without the complex conjugate, without the star. So this is just f. And that satisfies through this long equality chain that f star equals f, which is what we were trying to prove. Therefore, Hermitian forms are real. All right. Hopefully that makes sense. Put this marker away, where hopefully wow, it is tough to even put, I don't know if my thumb's getting weaker or if it's, that's a tough marker. Okay, it was the marker, it wasn't me. Now, to see how this actually relates to quadratic forms, right? Because Hermitian forms are just this slight generalization of quadratic forms. So everything that we can say about these guys, we can also say about quadratic forms. And this is the first thing to recognize about any quadratic form that we're working with. A quadratic form is going to be some scalar quantity that is inherently real valued. All right. So there will be no imaginary units floating around in that giant summation of terms, where the size of the sum, of course, depends on how many dimensions each of these guys are. Now, what we can do is we can take a step further and not just recognize that quadratic forms are real, but we can show how to write quadratic forms out in a more simpler fashion. And here's how we do that. What we can do is we can say that there is an inherent property of the matrix that's sandwiched in between quadratic forms. And maybe let me start by just writing out that now we're going to look at specifically quadratic forms. And I'll still write this scalar quantity f. And it will equal, rather than x dagger, I'm just going to write x transpose, assuming we're going to make the assumption that our vector is real valued. Now, instead of having a Hermitian matrix, H, I'm just going to have some real symmetric matrix, which I'll call A. Again, we could call it whatever we want, but we're just going to emphasize that this is real and symmetric. And then a vector X right here. Now, what I was trying to get at is that there's something we can say about real symmetric matrices that we've talked about a couple videos ago, but we might have forgotten, which is that real symmetric matrices are diagonalizable, which what that means is that this matrix A can be expressed as a product of 3 different matrices, which I will write out as V times D times V inverse, where V specifically is an orthogonal matrix whose columns are the normalized or the unit eigenvectors of A. Let's get back to the diagonalized or to the eigenvalues, eigenvectors section. So this is a column vectors of the normalized eigenvectors of A. And the matrix D is a diagonal matrix where each of the elements on the main diagonal is an eigenvalue of A. Okay. So what I want to do now to make some additional statements about quadratic forms is I want to just take this product, which A can be decomposed as, and to substitute it in to this matrix right here. So let's go about doing that. So now my quadratic form F is, we're still going to have X transpose out in the front. And then instead of A, we're going to write its diagonalized form, VDV inverse. And then we're going to have X on the left, or on the right, like that. Now, what we can do is rather than write out the parentheses, I started writing them out right there just so we could see the substitution. But I'm going to put the parentheses right here. And I can do this because matrix multiplication is associative, right? So I can put the parentheses wherever I want. So this is supposed to be V. We have D sandwiched in between the two, and then we have this quantity right here. If I look at this term right here in parentheses, I'm going to have a matrix times a vector, which is just going to give me a resulting vector. If we were to provide that vector with a name, maybe we'll call that vector y. So if this vector is y, let's try to see how we can write this vector right here. And maybe let me just be explicit that y is going to be v inverse times x. Like this. This quantity right here seems like it's kind of related to this quantity. And I'm almost going to give the answer away, but let's see why this is the answer. If this quantity is the vector y, then this quantity in parentheses is just the transpose of y. Let's understand why that's true. So y transpose, I am claiming, it's just the transpose of this, right? If this is y, or if this is y, then the transpose of y is v inverse x transpose. I'll move out of the way so we can see that, right? So just applying the transpose to both sides, and same idea as what we had right here. In order to apply the transpose to the product, I swap the order that they're written in and then apply the transpose individually. So I'm going to first have x being transposed. Conveniently, that's what we have here. And then I'm going to have v inverse transposed. And then this is where we would need to recall specific properties of these V matrices, these orthogonal matrices, or these matrices that inherently contain normalized eigenvectors. So what I'm about to say, this is just a true property of orthogonal matrices, and it's kind of how they're defined. I'll write it up here for orthogonal matrices. Ignore the handwriting. That if I have an orthogonal matrix V and I take its transpose, that's the exact same thing as taking the inverse of that matrix. Okay. So what that means is that if I take the inverse and then the transpose, that's like taking the inverse of the inverse or the transpose of the transpose. I'm going to get this original matrix that I had to start with, V. So I'm still going to have X transpose, and then I'm just going to have V. And that's exactly what I have right here. So what I'm trying to get at is this term right here in parentheses is really just Y transpose. So, whoops. This is Y transpose. So we can rewrite our quadratic form, F, as Y transpose times a diagonal matrix times Y. And then at this point, we can immediately understand the form that our quadratic form is written in because of the fact that D is a diagonal matrix. We're just going to have lambda 1, lambda 2, lambda 3, all the different eigenvalues along the main diagonal. And the way that this is going to get written out is this is just the sum, and we'll go through an example next, so this isn't so abstract. But if we're working in n dimensions, it's a sum from 1 to n, and we're going to have the main diagonal element, which will be the eigenvalue, lambda sub I, times the ith element of our vector squared. We have one factor coming from here, another factor coming from here. It's yi squared, like that. So the idea is that this all started with just saying that we have this general quadratic form, and we know that real symmetric matrices are able to be diagonalized. So this process of being able to take a quadratic form, a general quadratic form that we'll see in the next whiteboard, can be expressed more conveniently in this form right here. So hopefully the general idea makes sense, but I think we're really going to solidify the ideas by going through a specific example. All right, so we have an example here which will hopefully clarify kind of the general symbols that we were writing on the previous whiteboard. This is an example of a quadratic form, and I think this is good even just to see an example with actual numbers. We see that we have a sum of general terms where each of the individual terms has two factors of either an x or a y, which happen to be the components of the vector in the quadratic form. Okay. So this is what a quadratic form might look like, and if we were to write it in matrix vector notation, we could write it like this: x transpose times matrix A times x, where our vector x has components x and y, like we just mentioned, and A, as we can see, is a real value. All the elements are real, and it is a symmetric matrix, meaning if you were to take the transpose, you would get the exact same thing, right? Because you have a -2 here and a -2 right here. What I want, you might be saying, well, what's the example then, right? I mean, I'd be like, oh, this is it, and then we move on, right? But what I want to actually do is to show that when we diagonalize A, how we're able to rewrite this general quadratic form in a quote-unquote cleaner form, a form that's more convenient and often more desirable to work with in actual applications. Just one quick thing I want to mention too is just this term, just to make sure that we're clear about this. Notice that the factor, I have two factors of x here, two factors of y here, but I'm allowed to have these mixed factor terms as long as I have two total factors of elements coming from the vector. Those types of terms are allowed in a quadratic form. What we're about to see though is by diagonalizing this matrix A, we're able to decompose it in such a way that when we rewrite this quadratic form with slightly different coordinates, rather than x and y, maybe we'll put primes on them, we'll see that we'll be able to get rid of these mixed terms right here, the ones that contain x's and y's. Now, first step to doing that entire thing on the previous whiteboard is just to diagonalize the matrix. And I'm not going to go through that process again, that's what we've been doing in the previous section, but I'm just going to quickly just check and write out what the eigenvalues and eigenvectors are, and then we're going to see how to actually kind of incorporate them to rewrite this quadratic form right here. Okay, so if you were to diagonalize this matrix A right here, these would be the eigenvalues that you get, and here are the corresponding eigenvectors. Now, just to quickly mention that we include this factor of 1 over root 5 in the beginning because we want to normalize the eigenvectors. So that way the magnitude of each of these vectors is just 1. So let's see how, with this setup, we are able to rewrite this quadratic form F in this simpler form that we described earlier. So what we can do is we can first say that our matrix A, which is this real symmetric matrix, this 2, -2, -2, 5, can be decomposed as V, D, V inverse, where V is simply going to be the matrix whose columns are the eigenvectors. So we're going to have, I guess, this column and then this column vector and this column vector together as a matrix. I'm going to pull out the 1 over root 5 factor out front because that's constant among both of them. So this and then 2, 1, 1, -2. That's my matrix V. Then D is the diagonal matrix with 1 and 6 on the main diagonal. So 1, 0, 0, 6. And then finally just the inverse of this matrix right here. But because it's what's the word? Orthogonal. Because it's orthogonal, the inverse is just equal to the transpose of this matrix. And we know that the transpose, this matrix happens to be symmetric. So if we were to interchange the rows and the columns, we would actually get the same thing. So it turns out that for this specific matrix, V right here, V is equal to its transpose and its inverse, just coincidentally. So I can write out the same thing, 2, 1, 1, -2, like this. Now, to see how to write this in a simpler form, what we ended up doing is, if you remember the previous whiteboard, we said let's look at the quantity x v d v inverse x, or sorry, x transpose v d v inverse x, and then we define y to be this quantity right here, v inverse times x. So let's now just do that with the framework that we have. So I'll write over here, y is going to be v inverse, which just happens to be this same quantity as v. Again, that's not always true, it just happens to be true here. 1 over root 5, 2, 1, 1, negative 2. And then times my vector x, which is originally defined up here as x and y, like this. And if we were to just multiply this through, I'm going to have my factor of still 1 over root 5 out front. The constant's not going anywhere. And then for my top component, I'm going to have 2 times x plus 1 times y, or 2x plus y. And then for my bottom component, I'm going to have 1 times x minus 2 times y, or x minus 2y, like this. Okay. And as I was writing that, I realized some of this notation might be confusing because there are multiple x's and y's flying around. And I just realized that. I apologize for that. Is it too late to change this? I don't think so. Well, that's kind of a lot to change. So just to make sure that we understand what the notation is saying. X with the arrow over, this is the vector x, which has components scalar x and y. And then we're defining this vector y as the matrix times the vector x. And it just so happens that the vector y is also going to have components in terms of x and y. I hope that's not too confusing. If that is, I apologize. I realized that as I was writing this out. But assuming that makes sense, let's keep going. Okay. So then we already knew from the previous whiteboard that we were able to write, that we were able to write our quadratic form as this following summation. We were able to say that f was a sum going from 1 to n, because we were generally working with n dimensions. Then we had the ith eigenvalue times the squared ith component of our y vector. So now just relating that here, what f can be expressed as is we're going to have our n's now going to be set to 2, right? And our first eigenvalue is 1. So this is going to be 1 times the first component of y, of this vector, squared. So that's going to be 1 over root 5 squared, or actually let's just do this. We're going to have 2x plus y over root 5. That's the top component of my vector y. I'm going to square that, plus lambda 2, which is 6, times then the bottom component of this vector quantity squared, which is going to be x minus 2y over root 5 quantity squared. And now we can see that while we started with this quantity right here, then we end up with this quantity. It ends up being the same thing, except now it's 1 times some component squared plus something times another component squared. And while the symbols might look more confusing because we have fractions, square roots, and all of that stuff, the important thing is that we don't have any mixed terms. We don't have this times this. And you could symbolically just write this as y1 times y1 squared plus 6 times y2 squared, and all of a sudden it looks really pretty. But the idea is the overall structure, that there's no mixing with this summation where there is some mixed terms with this summation. So being able to eliminate that is a technique that we wanted to show here. Okay. So hopefully that makes sense. Now, to finish off the video, we're going to show that not only can we take a quadratic form like this, simplify it down to this structure right here, but we can take a more general structure called a quadratic and show that we can eventually get down to this type of structure as well. So I'm going to do that, and then we'll call it there. All right, so for the final definition of the video, we have this thing called a quadratic here. So let's go through it together, and then we're going to show how we can kind of rewrite what a quadratic is so it's in kind of that convenient form like that we've shown in the previous whiteboards. So we have right here that a quadratic is this n-dimensional surface that is defined by the zero of a real quadratic polynomial. And it is written like this, where the first term is this thing that looks like the quadratic form that we've been looking at so far. Or I shouldn't say it is, because a quadratic form is specifically a real symmetric matrix. A here is just any arbitrary m by n matrix. Then we also have a term that is quote unquote linear in the vector x. There are two factors of the vector x here, so I'm quote unquote calling this quadratic in the vector x. This would be linear in the vector x. And then c is just going to be some scalar quantity, because after all, this quantity is a scalar. When I take the transpose of a vector, or if I take a row vector times a column vector, that gives me a scalar. So this should also be a scalar. So I have a scalar plus a scalar plus a scalar. I'm adding things of the same dimension, and then I'm setting that equal to 0. Okay. So this quantity right here is simply what a quadratic is mathematically. And now what we're going to do is we're going to show how we can manipulate this to get it to that nice, convenient form. So the first thing that we're going to do is we're going to show that this matrix A can be decomposed into symmetric and anti-symmetric counterparts. And here's how we would go about doing that. So let's just say I have a general matrix A. It's some m by n matrix. And this would be the ijth element of it. Or I'm going to use element notation to show this. What I can do is I can break this up into two quantities. I can write A, or 1/2 aij plus aji. And then I can also add plus 1/2 aij minus aji. This quantity right here is inherently a symmetric matrix. If I were to write, if all the elements of just this quantity, 1/2 aij plus aji, if I were to make a matrix out of elements that look just like this, I would have a symmetric matrix. So I'm just going to call that Sij. This is the symmetric component to this decomposition. Then for this term right here, if I were to compose a matrix with elements that look just like this, maybe I called it, I don't know, Tij, then the matrix T would be purely anti-symmetric. All right, and hopefully it makes sense too that just by taking this term plus this term, that gives us Aij back, right? We have 1/2 Aij plus 1/2 Aij giving us Aij, the left-hand side. And then we have 1/2 aji minus 1/2 aji. So the aji terms cancel and the aij terms add constructively to give us this right here. Basic idea, you can take any m by n matrix and decompose it into the sum of a symmetric matrix plus an anti-symmetric matrix. Now, question is, why is that important, right? And the reason why that's important is because we can say, well, let's take this quantity right here, x transpose ax, and just rewrite the matrix A as the sum of a symmetric and anti-symmetric counterpart. So let's do that. You know what, because that won't take too much time, I'm going to just do that right here, and then potentially erase that. But we're going to have this term, x transpose ax, and I'm going to rewrite this as x transpose s plus t times x, like this, where s is symmetric, t is antisymmetric. And then we're just going to distribute the vectors across. So this should end up equaling x transpose s times x, x transpose s times x, plus x transpose t. I should have used another letter besides t, huh? But x transpose times the matrix t times x. And what you could do is you could ultimately show that this quantity, x transpose times an antisymmetric matrix times x, will always equal 0 for any antisymmetric matrix. I'm not going to go through proving that, but what I'd recommend doing if you're not convinced is just to take the 2 by 2 case of the matrix T, and then two-dimensional vector x, and then just take this quantity and you'll see that it's 0, and hopefully that's convincing enough. If not, then go find the proof online for why this quantity must be 0 in the general case, but I don't feel like doing that. The point of this is that this term is going to go to 0 based on the fact that T is an antisymmetric matrix. And that is important because for any real n by n matrix A, when decomposed in this form, in a symmetric plus antisymmetric form, the antisymmetric part goes to 0, leaving us with just the symmetric part. So hopefully I'm okay to erase the decomposition. And that tells me that my original equation for the quadratic, this guy right here, can be rewritten. So now my quadratic form term, or now this term that's quadratic in x is a quadratic form. I'm going to have x transpose. I'm going to have a real and symmetric matrix right here, hence what makes it a quadratic form, times x. And then the same remaining equation, right? So then I'm going to have b transpose times x plus c gives me 0. Hopefully that makes sense. And admittedly, I know I'm just stating that without proving that. But some of the stuff we're proving here, some of the stuff we're not. So either take my word for it or look it up yourself. I promise I'm not lying on that part. So what can we do now? Well, we know that a real symmetric matrix can be diagonalized, so we can write S as VDV inverse. And then we just plug it in, right? So then we're going to get, for our first term, X transpose VDV inverse. But if, we'll keep it like that. VDV inverse. I could write VDV transpose because V is orthogonal, but I'll leave it as V inverse. So we have X transpose VDV inverse X plus everything else. So then we're going to have B transpose times X plus C gives me 0. Now, this might get, I was hesitant when I was going through Dexter's notes on seeing whether I thought his notation would be good or not. He ends up using a lot of primes, but I think the primes actually make sense in this case because it shows how many times we're changing the form of our vector. And by vector, I mean this vector x right here. Okay. So I think I want to stick with the notation that he has here. What he does, what we were doing, I should say, was we were defining this quantity v inverse times x as a new vector y. He's going to instead define it as a vector x prime. So he's going to now say, if I have this vector x prime, I'm going to have that equal this, like this. So then if I were to rewrite this equation, so now it's written not in terms of the original x vector, but it's written in terms of this new vector x prime. This is what I would get. We've already shown in the previous whiteboard that the quantity x transpose v is really just this new vector, this x prime vector transposed. I have my diagonal matrix D. Then the definition of x prime, v inverse x prime, like that, plus, and I'm going to have b transpose here, but I want to, and I could just leave b transpose like that, but I want to be able to rewrite x in terms of the new prime coordinates. So let's do that for a second. I'm going to write, let's just write x at, or rather than x, I'm going to write x prime. How do I want to do this? Here, just wait with me for just a second. What I'm going to do is what I'm actually going to do is I'm going to take this quantity, B transpose. I have it in my head, just trying to say it in words, right? And I want to sandwich two matrices together so that I'm able to rewrite x in terms of the prime coordinate. That's what I was trying to say. So I know that if I want to be able to write x in terms of the prime coordinate, I'm going to need a v inverse x right here. So what is going to cancel out with v inverse? Well, just the matrix v. And you can imagine, v times v inverse gives you the identity, leaving you with your original b transpose x. And then c is already a scalar, so we don't need to do anything with that. But now what we can do is we can rewrite this equation. I can have my same first term, x prime transposed dx prime, plus, and what I'm going to do is I'm going to define b transpose times v to be a new version of the b vector. We had this original real n-dimensional vector b, but now I'm going to make a new definition for b, a primed version for b, and that's simply going to be b transpose times v, like this. So now, let me make sure I get this right. This is going to be the transpose version of b prime is going to be this quantity right here, right? So this is a row vector. I need the transpose there, so that way I have b prime transposed times v inverse x, which is x prime. The reason, by the way, I want the transpose here, so I can take a row vector times a column vector. That product still gives me a scalar, so I'm adding up scalars of this equation. So we're going to make that definition, plus c gives me 0. And at this point, we fully transformed our equation from a starting equation with just x vectors now to the new primed counterpart. We're going to make one more coordinate transformation, but just to make sure I get that one right, I'm just going to refer back to Dexter's notes, write that down here, and then we're going to finish out showing that we can take a general quadratic and write it in this very convenient form. Okay, so we have this final coordinate change now going from the primed coordinates x prime to this second primed coordinates to indicate a second coordinate change, where we have x double prime equals x prime plus 1/2 d inverse times b prime. And I just realized that, because this is at the bottom of the board, what I should probably do is write out this equation right here, which is the equation in the single primed coordinate system, as well as this new definition for the double primed coordinate system up at the top, so then we have room to evaluate this and then just show that we can take our starting quadratic and rewrite it in this simplified form. So I'll probably leave this, and this up on the board and erase everything else to finish up the video. All right, so we have this double primed version of x, which will be the final transformation of this x vector. And what we're going to do is we're going to take this definition and we can just isolate for x with a single prime. And if we were to do that, we would get x prime equals x double prime minus 1/2 d inverse b prime. And the reason for doing that is because we can now take this definition for x prime, plug it in everywhere where there's an x prime in the equation, and then simplify. And just a heads up, this is going to probably take a little while, but eventually we'll get to the punchline. So this should all work out in the end, in theory. So I'm going to have this quantity transposed. So what I'm going to do is I'm just going to write a big set of parentheses to say this difference of vectors now. So x double prime minus 1/2 d inverse b prime, that is transposed, times my matrix D, times x prime, which is this thing in parentheses. So x double prime minus 1/2 d inverse b prime, like this, takes care of the quadratic term. Then I have plus b transpose, or b prime transpose, times x prime, which again is this quantity. And again, the reason for doing this is so we can get an equation solely in terms of the double primed coordinate. And then everything should work out. So we have b prime transpose times x prime, and then plus c equals 0. So to start manipulating this, I'm just going to take this quantity here in parentheses and apply the transpose to both of the terms. And when I do that, I'm going to have my first term, x double prime transposed, minus this product transposed, which is 1/2 b prime transposed. And then, right, because I'm interchanging the order when I apply the transpose. And then I have D inverse, but D is a diagonal matrix, so its inverse is also a diagonal matrix. So when I take the transpose of a diagonal matrix, I just get the same thing back. So I don't even need to write D inverse transpose. I just know that it's going to be the same thing as D inverse. This whole term, or quantity, is in parentheses. Then I'm going to distribute D across this set of parentheses. So now here I'm going to have D x double prime minus 1/2, because the constant can go out front. Then I have D times D inverse, which cancels out, leaving me with just B prime. Things are starting to simplify. Right? Then here I'm going to have plus B prime transpose x double prime. It's a lot of primes. Minus 1/2 B prime transpose D inverse B prime, and then plus C equals 0. And then the last thing we have to do is really just to distribute everything across, and stuff will work itself out. So I'm going to have x double prime transpose dx double prime transpose d, is that right? Yeah, dx double prime. And this is good too, right? Because this is the form that we really want to get things in. Minus 1/2 x double prime transpose b prime. Then minus this quantity, which is minus 1/2 b prime transpose. Then we have d inverse d, those cancel out, and we are left with just x double prime. And then we have, let's see, this is plus 1/4 b prime transpose, so b prime transpose d inverse b prime, like this. That should take care of expanding that product out. Then we have just these remaining three terms. So plus b prime transpose. I really hope I'm not making a typo at some point. X double prime minus this term, minus 1/2 b prime transpose d inverse b prime. Can I fit that in there? Sure. Plus c equals 0. You can see why I want to erase the board, right? And now, what we can do, it might not initially seem obvious here, but let's take a look at this term, and this term. I'll underline them, or I'll circle them. So we're gonna have this term this term and this term right here. Notice that we have x double prime transpose b prime transpose x double prime, and then b prime transpose x double prime. But inherently, this operation is going to produce a scalar, right? And because these are real valued, this is essentially the dot product between x double prime and b prime. And the dot product, at least when working with real vectors in Rn, is symmetrical. It doesn't matter the order in which we apply them. So whether we write the x vector first or the b vector first, it actually doesn't matter. This overall quantity is going to be the same. So we have minus 1/2 of this quantity, minus 1/2 of this quantity, plus a whole part of that quantity. So this term cancels, this term cancels, and this term cancels for that reason. And then what we're left over with is we still have this first term, x double prime transpose dx double prime, plus, and I think now that I'm looking at this term is 2 factors of x right here, and then the remaining terms have no factors of x. They're effectively a constant, they're independent of x. So what I'm going to do is I'm just going to call, and this is what Dexter does, he says this is the left-hand side, everything depends on x. The right-hand side will be everything that is independent of x, regardless of what we would have. Minus 1/4 times this plus 1/2 times this minus c on the right-hand side. Just absorb all of that into a single constant k. And what we've just shown through, admittedly, a decent amount of algebra, but hopefully it wasn't too much, that we can start with a general quadratic and show that we can end up getting it into a nice convenient form where we have some version of a coordinate. We just had to go through 2 coordinate transformations to get to a double prime coordinate times a diagonal matrix, and that's the key, the fact that D is diagonal times the vector x double prime. Only difference now is that rather than just having this single quantity without an equal sign, what we've had with general quadratic forms, now we're just including an equation when working with quadrics. So what we're going to see in the next video, because that's going to be all we cover in this one, is that we're going to start looking at specific instances of this type of equation right here, and that's going to be the kind of the springboard into conics and conic sections. So yeah, that's all I got. Thanks so much for watching, and I will hopefully see you guys in the next one.